8.2 area of a surface revolution. Sidebar figure circumference 2 pi r. There's a cut along h. And we have h by 2 pi r. Back to the text. A surface of revolution is formed when a curve is rotated about a line. Such a surface is the lateral boundary of a solid of revolution of the type discussed in sections 6.2 and 6.3. We want to define the area of a surface of revolution in such a way that it corresponds to our intuition. The surface area is big A. We can imagine that painting the surface would require the same amount of paint as does a flat region with area big A. Let's start with some simple surfaces. The lateral surface area of a circular cylinder with radius r and height h is taken to be big A equals 2 pi r h, because we can imagine cutting the cylinder and unrolling it as in figure 1 to obtain a rectangle with the dimensions 2 pi r and h. Likewise, we can take a circular cone with a base radius r and slant height l, cut it along the dashed line in figure 2 and flatten it out to form a sector of a circle with the radius L and central angle theta equals 2 pi r over L. We know that in general the area of a sector of a circle with radius L and angle theta, is 1/2 L squared theta. See exercise 7.3.35. And so in this case, the area is big A equals 1/2 L squared theta equals 1/2 T squared open 2 pi r over L close equals pi RL. Therefore, we define the lateral surface area of a cone to be big A equals pi RL. Figure 2, length L, the radius and the cut 2 pi r, angle theta, length L. What about a more complicated surfaces of revolution? If we follow the strategy we used with arc length, we can approximate the original curve by a polygon. When this polygon is rotated about an axis, it creates a simpler surface whose surface area approximates the actual surface area. By taking a limit, we can determine the exact surface area. The approximating surface then consists of a number of bands, each formed by rotating a line segment about an axis. To find the area, to find the surface area, each of these bands can be considered a portion of a circular cone, as shown in figure 3. The area of the band, or frustum of a cone with slant height L and upper and lower radii r sub 1 and r sub 2 is found by subtracting the areas of the areas of two cones. Equation 1, big A equals pi r2 open L sub 1 plus L close minus pi r sub 1 L sub 1 equals pi open bracket open r sub 2 minus r sub 1 close L sub 1 plus r sub 2 L close bracket. See figure 3. You have L and L sub 1 and R sub 2 and R sub 1. back to the text. From similar triangles, we have uh, L sub 1 over R sub 1 equals L sub 1 plus L over R sub 2. Which gives R sub 2 L sub 1 equals R sub 1 L sub 1 plus R sub 1 L, or open R sub 2 minus R sub 1 close L sub 1 equals R sub 1 L. Putting this in equation 1, we get big A equals pi open R sub 1 L plus R sub 2 L close, or equation 2, big A equals 2 pi R L, where R equals 1/2 open R sub 1 plus R sub 2 close is the average radius of the band. Sidebar, figure 4, 4A, and 4B. 4A is surface of revolution, where y equals f of x, and B, approximating band, p sub naught, big P sub naught as a point, big P sub I minus 1, big P sub I, we have y sub I, and big P sub n. Points A and B. Back to the text. Now we apply this formula to our strategy. Consider the surface shown in figure 4, which is obtained by rotating the curve y equals f of x, where x is greater than or equal to a and less than or equal to b. About the x-axis, where f is positive and has a continuous derivative. Redoing that sentence, consider the surface shown in figure 4, which is obtained by rotating the curve y equals f of x, where a is less than or equal to x and x is less than or equal to b, about the x-axis, where f is positive and has a continuous derivative. In order to define its surface area, we divide the intervals open bracket a and b close bracket into n subintervals with endpoints x sub naught, x sub 1 through x sub n, and equal with delta x, as we did in determining arc length. If y sub I equals f of x sub I, then the point big P sub I open x sub I and y sub I close lies on the curve. The part of the surface between x sub I minus 1 and x sub I is approximated by taking the line segment big P sub I minus 1, big P sub I, and rotating it about the x-axis. The result is a band with slant height L equals the absolute value of big P sub I minus 1 and big P sub I, and average radius R equals 1/2 open y sub I minus 1 plus y sub I close. So by formula 2, its surface area is 2 pi times y sub I minus 1 plus y sub I over 2 times the absolute value of big P sub I minus 1, big P sub I. as in the proof of theorem 8.1.2, we have the absolute value of big P sub I minus 1, big P sub I, equals the square root of 1 plus open bracket f prime of x star sub I close bracket squared delta x, where x star sub I is some number in open bracket x sub I minus 1 and x sub I close bracket when delta x is small. We have y sub I equals f of x sub I is approximately equal to f of x star sub I, and also y sub I minus 1 equals f of x sub I minus 1 is approximately equal to f of x star sub I, since f is continuous. Therefore 2 pi y sub I minus 1 plus y sub I over 2, the absolute value of big P sub I minus 1 big P sub I is approximately equal to 2 pi f of x star sub I times the square root of 1 plus open bracket f prime of x star sub I close bracket squared delta x. And so an approximation to what we think of as the area of the complete surface of revolution is equation 3. The sum from I equals 1 to n of 2 pi f of x star sub I times the square root of 1 plus open bracket f prime of x star sub I close bracket squared delta x.